Network demands are scaling rapidly. Gigabit bandwidth is the baseline for modern digital infrastructure, but the physical systems we rely on to deliver that data are hitting rigid logistical limits. Radio frequency networks, or RF, are reaching a saturation point. The available spectrum is highly congested and tightly bound by regulatory constraints, capping the total volume of data that can be delivered through the air. While physical fiber optics provide necessary bandwidth, deploying them in dense urban environments requires physical trenching. This forces providers to navigate complex municipal regulations and absorb the massive financial costs of laying cable under city streets. Free Space Optical Communication, or FSO, provides a synthesis. It delivers the data capacity of fiber optics using the wire-free deployment of an RF network. The mechanism is entirely optical. An FSO link transmits data by sending high-intensity, coherent light beams directly through the atmosphere, requiring a strict line of sight between the source and the destination. Maintaining these high-capacity data rates requires forcing delicate optical signals through an actively hostile and chaotic transmission medium, the open air. Building this link starts with the transmitter. Its first task is converting an incoming stream of electrical data into an optical signal. This requires highly coherent light sources, typically laser diodes or vertical cavity surface-emitting lasers, known as V-cells. V-cells offer a specific architectural advantage. Because they emit light perpendicular to the semiconductor surface, they can be arranged in dense arrays. This allows for spatial multiplexing, which increases the total output power of the transmitter. Light is encoded through modulation. The simplest method, on-off keying, uses amplitude, on for a 1, off for a 0. Relying on amplitude makes it vulnerable to noise. Interference distorts the waveform, breaking down the signal. FSO systems manage this by utilizing pulse position modulation, or PPM. Instead of relying on continuous amplitude, PPM encodes multiple bits of data based on the precise timing of a single pulse within a fixed timeframe. Before this modulated light leaves the transmitter, it passes through a collimating lens. This hardware gathers the naturally divergent light and forces it into a strictly parallel beam, minimizing signal spread over long distances. The transmitter engineers a structured, noise-resistant optical package. The signal is now prepared for the physical chaos of free space. Once the beam leaves the aperture, the physics of the link demand an unbroken line-of-sight propagation path to the receiver. Any physical obstruction severs the connection entirely. But the open air itself presents the first major threat to the signal, scattering. As the beam travels, it strikes particles in the atmosphere. Microscopic gas molecules cause Rayleigh scattering, which deflects shorter wavelengths of light. But when the beam strikes larger particles like dust or water droplets, it triggers Mie scattering, fracturing the beam's trajectory. Fog droplets match the size of infrared wavelengths, diffusing the beam and stripping its capacity. Additionally, absorption by water vapor and carbon dioxide drains energy directly from the photon stream, weakening the overall signal. Because this absorption is predictable, engineers must select narrow operating wavelengths that slip through specific atmospheric transmission windows to avoid total signal loss. Even if the beam survives scattering and absorption, it faces a third highly dynamic threat, atmospheric turbulence. The atmosphere contains constant thermal gradients. Varying air temperatures create pockets of differing air densities, which alter the local refractive index according to Snell's law. These shifting temperatures force the laser beam to bend and wander. This creates wavefront distortion and a rapid signal fading effect known as scintillation. The atmosphere acts as an aggressive, multi-layered filter. It actively scatters, absorbs, and warps the data stream before it reaches its destination. By the time the optical signal strikes the receiver, it is attenuated, physically distorted, and buried underneath ambient background noise. The receiver must salvage the beam. A precision focusing lens concentrates the weakened photons, while optical filters block out solar interference and ambient light. The core mathematical objective at this stage is maximizing the signal-to-noise ratio. The incoming data must be distinguishable from the background interference. Two types of noise threaten that ratio: thermal noise generated by the electronics, and shot noise, which is caused by the discrete, irregular arrival of the incoming photons themselves. To extract the data, the system relies on a photodetector to translate the surviving light back into an electrical current. While short-range systems can use basic silicon photodiodes, pulling a degraded signal out of a long-distance FSO link requires the avalanche photodiode, or APD. The APD utilizes a process called avalanche multiplication. A single, faint incoming photon strikes the detector and triggers a cascading release of electrons, creating a large electrical spike at the output. This internal quantum-level amplification boosts the signal strength. It generates an electrical response large enough to overcome the inherent thermal and shot noise inside the receiver. Receiver engineering is essentially an active salvage, using hypersensitive hardware to amplify the structural order still hidden within atmospheric chaos. Zooming out from the individual components reveals a unified optical signal processing ecosystem working in concert. The transmitter constructs a resilient signal, the beam pushes through the scattering and thermal turbulence of free space, and the avalanche photodiode captures and multiplies the surviving photons. Engineers increase this capacity even further using wavelength division multiplexing. By utilizing different frequencies of light, they stack multiple distinct data streams into a single beam. This allows FSO to act as a crucial backbone for specific high-stakes applications, including 5G backhaul, secure military communications, and rapid connectivity during disaster recovery. By applying these principles to the atmosphere, engineers have developed a system that delivers fiber-level speeds through the air, providing a high-capacity alternative in environments where physical cables cannot go.